My guest today is Nicola Scafetta.
I am a professor of climatology at the University of Naples, Federico II, and so I am in Italy. This is the title of my presentation, Understanding Climate Change. So I would like to talk to you about this topic that is a hot topic, and we will discuss several issues. In particular, we would like to understand whether climate models used for interpreting climate change are credible, and whether there are other interpretations that should be properly taken into account. Now, the first thing that is usually I start my presentation by showing a map like this one. This is the temperature anomaly on July 11, 2023. And what we see is that there are some regions that are warmer than the average occurred in 1979-2002 base, and other regions that are colder. So this is weather. This is weather. And we would like to talk about climate. The first thing is to understand the difference between climate and weather. Because many times what people show are pictures like the one that you can see here. So you can see some floods, you can see some tornado, you can see some fire, and so on. And many of these pictures don't capture the concept of climate, but they capture the concept of weather. So the weather is something that is happening every time. So it's the state of the atmosphere in any moment, and it varies a lot every minute. And so people usually are able to notice whether or not the weather is changing. On the contrary, climate is something that changes very, very little. It's very difficult for humans to detect climate change because we are talking about very small numbers. Now, regarding the climate of the Earth, this is a picture that summarizes what happened during the last 542 million years. And here we are more or less at this level. Then we go back in time. So we have 1,000 years, 2,000 years, 5,000 years, 10,000 years, 500,000 years, and then 1 million, 2 million, 10 million, 100 million, and so on. So what we are able to see from this picture is that the climate of the Earth has always changed. So, sometimes the temperature were significantly colder than today. So this, for example, these were the ice ages. And other times, like in this case here, we had temperatures far higher than today. So it is normal for the Earth to have a change in climate, that it is normal to have periods, hot periods and cold periods. In this picture that is below here is a kind of interpretation of what you see on the top. So practically here there are several. It's a power spectrum of the records that is above, and what we see here is that there are many cycles. Essentially, climate change is characterized by a lot of oscillations. So there are some oscillations that are very, very long oscillations here, about 150 million years, which are essentially the one that we see here. And then there are other oscillations like this one, which are known as the Milankovitch cycles, the 400,000 years, 100,000 years, 41,000 years, 21,000 years. These are the oscillations due to the orbital variation of the Earth, and can be recognized very easily here during this period, where we have this nice 100,000 oscillation that characterize the last 500,000 years. And then there are shorter cycles. These cycles are cycles of about 1,000 years. We have and then you have shorter cycles like 200 years, 115 years, 60 years, 20 years, and so on until the annual cycle, that is the shortest cycles that everybody knows. And so this picture tells us that climate is very complex, but it is made with a lot of oscillations, and practically all of these oscillations have a astronomical origin. So in particular, these long oscillations appears to be related to a galactic forcing, so associated to with the journey of the Earth around the galaxy. Then these oscillations, as I said before, are related to the orbital forcing, so changing the orbit of the Earth. And then we have these shorter cycles, which very likely are all solar cycles. So I will show you these are actually all related to solar activity, or in any case to some astronomical behavior. Thus, we have a changing climate, and a climate that is changing with several astronomical solar oscillations. So this is what happened normally. Now, during the last 150 years, we have seen a warming. Okay, so this is the global surface temperatures that are usually used in climatology, and we see here that the temperature has rose by about 1 degree. 1 degree in about 150 years. So this is what we know as global warming. So there is no doubt that the Earth has warmed during the last 150 years, so everybody agrees on this data, more or less. But the big issue is to understand what has caused this warming. And the issue is whether nature or humans have been responsible of this warming. So, and this is a big issue, the big issue. Now, let us see how this record is interpreted or can be interpreted. Now, usually this record is interpreted by the IPCC, so Intergovernmental Panel on Climate Change of the United Nations, is interpreted using climate models. Now, we will discuss a little bit how these models are used. So these models are essentially are supposed to simulate all physics of the climate system, and therefore they are supposed to simulate climate change. And the hypothesis of the models is that there are a set of radiative forcings that are changing the climate system. And therefore, people use these models, they force these models with a set of radiative forcing, and they essentially get this gray line, that are here shown here. Then the same models are used for creating projections for the future. And so climate change projection for the future. So we have several scenarios that are supposed, and so these are scenarios associated with different amount of global emissions. And therefore, according to these emissions, the climate will warm more or less. So for example, this purple scenario is a very worrisome because it predicts a very strong warming. Then the green one essentially supposes that the CO2 emission stops in 2030, something like that, and therefore the climate will stabilize. Now, these projections are used then are compared with a different kind of models, which are the models that study the vulnerability of various systems in Earth systems. And therefore, what this model claim is that if the temperature will rise too much, then several systems will start to be vulnerable. So practically, essentially, these colors, we have that the gray color, there is no problem at all. The orange color means that we can adapt to climate change. But the red colors means that we are not really able to adapt. And so these models show that by 2050, around 2050 here, the temperature will rise above 2 Celsius degree relative to the pre-industrial time. Pre-industrial time would be this baseline here. So it will rise 2 degrees from this line, And if it rises above 2 degrees from this line that is here, if it rises 2 degrees, we will see here that there is some system, in particular the natural ecosystems, that will start to suffer for global warming. And or water security will suffer, or coastal community will start to suffer for global warming. And therefore, people say that there is a serious risk for the Earth that we can have serious problem in the future if we do not do something to mitigate the climate change, because according to this hypothesis, the temperature should not rise above 2 Celsius, no? So because it rises too much, it will cause several problems that humans will not be able to solve with adaptation, in particular in the poor countries. So this is what has been done. So this is the position of the IPCC. The climate models are telling us that if we don't do practically nothing, if we do not mitigate climate change, the temperature will rise very, very fast, and this can create big problems to the world. So this is so we need to do something to mitigate the climate change. Now, however, the scientific problem is to understand whether or not we can truly trust these models and whether or not we can truly trust these projections. Because the alarm is related to these projections that are created by these models. So we need to be sure that these models are correct. They are really interpreting the true climate of the Earth. And so let us see what the IPCC claims, okay? And then we will attempt a critique of the IPCC position. Now, the IPCC essentially use the models in the following way. So he does the simulation in two ways. In the first way, the simulations are run using only natural forcing. So natural forcing are related to solar activity changes and volcanic eruption. Okay, so and what the models say is that if we use only the natural forcing, the temperature should have remained more or less constant during the last 150 years. So here we have this simulation here, these simulations here. You see that the warming in 2020 is more or less similar to what happened in 1850. So according to the models, natural forcing should not have produced any warming. The temperature should have remained constant for 150 years, for more than 150 years. Then the same models are forced using all forcing. So we have the anthropogenic forcing, like CO2, like those related to CO2 emissions, and then plus the natural one, so plus solar and volcanic. When the simulations are run with all this forcing, so we get this kind of simulations, and these simulations show that show a warming that approximately reproduces the black line. The black line represents the data. So the IPCC concludes that natural forcing are not able to produce any warming, while the warming is produced by anthropogenic force. And therefore, it concludes that 100% of the warming since the pre-industrial era is anthropogenic. Now, this picture, this argument appears very solid, but these arguments actually is not solid at all. In fact, the scientific methods requires that model simulations be tested against the data, against the observations. This is what the scientific method tells us. And in this case, we cannot claim that the scientific method has been applied or satisfied, because this prediction of the model, so here the model is predicting that without anthropogenic forcing, so without humans, the temperature would have remained constant. This prediction cannot be verified for the simple reason that we do not have another planet like the planet without humans, where we could collect the temperature data and verify that without humans the temperature would have remained constant, for 150 years. Therefore, this argument actually it does not satisfy the scientific method requirements, and therefore does not say anything, does not prove anything. It only proves that these models are not able to produce the warming without anthropogenic force. But perhaps the models are wrong. They are missing some important ingredient, some important natural forcing, which could explain at least part of this warming. We do not know at the moment, but according to the scientific method, this test that does not satisfy the scientific method, because we cannot test this prediction. We cannot test this prediction here. Okay. Now, so we need to analyze the models in more detail. Now, the climate models. There are many climate models. The climate models, the latest climate models are this CMIP6, so it's the sixth version of this group of models. And these models actually are very different from each other. So here we have about 40 models, and created by different groups around the world. And this picture shows us that actually these models are very different between them. In fact, these numbers, what are these numbers that I show here? These numbers are what are called the equilibrium climate sensitivity. The equilibrium climate sensitivity is an estimate of the steady state global warming when CO2 doubles in the atmosphere. So CO2 is a greenhouse gas. So it is. So if we increase CO2 concentration in the atmosphere, the greenhouse effect should increase. If we double the amount of CO2, this implies an increase of radiative forcing of about 3.7 watts per square meter. So there is this increase of radiative forcing, and this radiative forcing will induce a warming of the climate system. However, when the models are run with the same forcing, so with this 3.7 increase of the radiative forcing, we have some models that predict a warming of just 1.8 Celsius, and then we have other models like this one that predicts about 4 Celsius, and then finally we have these other models here that predicts about 5.6. So we have 1.8, 5.6. This means that these models are very uncertain. Okay, so then they do not know what CO2 is able to do to the climate. So it is true that CO2 is a greenhouse gas. It is true that if we increase CO2 concentration, there should be a warming. But nobody really knows how much warming. The same climate models used for interpreting climate change tell us very different things, because it is obvious that 1.8 is too small relative to 5.6. So this window, this range is too large to claim that we truly understand climate change, that we truly understand what CO2 is making to the climate. Therefore, it is very likely that most of these models are wrong. Just some of them can be right. So, for example, if I have divided these models in 3 groups, models with a high equilibrium climate sensitivity, models with a medium equilibrium climate sensitivity, and models with a low equilibrium climate sensitivity, it is obvious that if these models are more or less correct, then all these others are wrong. But if these models are correct, then all these others should be dismissed. So we cannot assume that all these models are correct, because the difference between them is too big. So what I did, this is one of my papers, is to test the ability of these models of predicting climate change since 1980 to 2023, okay? And I divided the models in three groups, okay? In these three groups that are here. It's 1, 2, and 3. So these three groups here. And what we see here is that here we have in black, we have the data, the actual observation, and the colored lines are the simulations from the models. This yellow area is the same thing. This is the range plus minus 1 sigma average. So the yellow area represents actually this distribution of models. And what is seen here is that the models with a high equilibrium climate sensitivity appears to run too hot. Okay, so it is evident that these models are running too hot. Now, I am using this period since 1980 because these data are supposed to be very accurate, so there are very small errors and so on. We have coverage from the satellites and so on, and therefore these data are supposed to be very accurate. And what we see here is that these models, the high sensitivity models, are actually running too hot. It's very clear that the yellow area is above the black line. Here we have the medium model. Here we have the medium model. And therefore, what we have here is that the yellow area is appears still too hot. It's still above the black line. Okay, sometimes the black line is within the yellow area, but these are just spikes. And therefore, also these models, the medium equilibrium climate sensitivity models, appears to be running too hot. Then, when we use the low equilibrium climate sensitivity models, we get this graph. And in this case, it appears that the yellow area agrees with the actual warming observed in the climate system. Therefore, from this, so these dots are actually the single models, the average of the single models. Okay, so what we see here, that is for high sensitivity models, these models produce too much warming from 1980 to 2020. Okay, so they predict too much warming. Only the low sensitivity model, only these low sensitivity models appears to more or less agree with the data which are inside this range. The data are inside more or less this range. Okay, so the other models usually run too hot. Therefore, I concluded from this study, I concluded that all these models, so the high and the medium sensitivity models actually do not appear to be sufficiently good to interpret the climate change, because they are predicting too much warming, and therefore at most we need to use these models, the low sensitivity models, to do what? To do the projections, for the future. Now, before arriving to that point, however, here I put another record. Here I put another warming. I will discuss this warming later in this talk, because this warming, this is the warming between this period and this period here. Is the warming between these two periods, okay? This warming is the warming produced by the satellite records. So these are the warming produced at the surface, so reported by the global surface temperature. This is instead the warming reported by the lower troposphere temperature record, which are obtained with the satellite. Now, you see here that the satellite records show a warming that is significantly lower than what is shown by the surface record. So we will discuss this issue later. But this difference is very big. And since the surface record should have more or less the same warming of the lower troposphere, this difference is very problematic. The big difference is very problematic. So problematic that if these data are correct, if this is the real warming, then we will discuss why this might be correct. All models appears to be running too hot, and therefore all models appears that needs to be dismissed. Now, curiously, this is not something just produced by my research. This is actually produced also by the IPCC. This is a picture 3.10 of the IPCC of the R6. It's the report of the latest report of the IPCC. And what we see here is a comparison of the warming produced by the climate models against the actual data. So here there are three ranges. So the period 79-2014, the period 79-97, and the period 98-2014. Now the black lines are the data. The black lines are the data. And what we see here, and the orange are the models. The orange are the models. And what we see here is that above the tropics, these are the vertical profile of temperature trends above the tropics. What we see here is that the models produce a warming which is clearly above what is actually observed. So, for example, during this period, we do not get too much warming in the troposphere. In the troposphere, so this is the top of the troposphere. This is the bottom of the troposphere. So we see that we don't see any warming, any significant warming in the troposphere, while the models have produced a big warming that is like this. So the models actually are failing to reproduce the warming observed during these 40 years in all vertical profile of the troposphere above tropics. This is very problematic. This is very important results because the theory of the greenhouse theory suppose that above the tropics, in particular at the top of the troposphere, so more or less in this region, the greenhouse gas theory predicts this warming, this significant warming that we see in these models predicted. And this warming actually is not observed. So this warming is due to the fact that according to the greenhouse gas theory, the first thing that should warm is the atmosphere, because what happens here is that the greenhouse gases absorb the infrared radiation produced by the surface, and therefore the atmosphere warms up. And then it is the warming troposphere that warms also the surface. So the first thing that warms up should be the troposphere. But the observation tell us that above the tropics, particularly during the last 20 years, there has been very little warming, and the models are completely off from this prediction. So this is another evidence that the models have huge problems, are having huge problems. In any case, if we look again to these results that where I am using the surface temperature, only the low equilibrium climate sensitivity models might be correct if we exclude the data from the troposphere. And if we use only the low sensitivity models, by 2050, these models predict this kind of warming according to different scenarios. And now, what is this problem? So these are the predicted warming from these models. And what we see here is that these scenarios are very different from each other. But according to some studies, the scenario that is more likely correct, the scenario that is more realistic is this one, is the green one, the SSP2 4.5, is this scenario here. And this scenario predicts this green range. As we see here, this green range is within the orange color of the risk. So this is the a global aggregated impacts. So it's a measure of the risk. And this color is orange. So this green area, the range, it falls within this yellow range. So it is below 2 Celsius degree. This means that we will not cross the 2 Celsius degree, and therefore we can easily adapt to climate change. Therefore, if only the low sensitivity models, are used, and we adopt only the scenario that is more realistic, this one, then there should be no alarm. There should be no alarm. The alarm is not justified because these models predict only a moderate warming. Therefore, on the base of these results, okay, I don't believe that there is climatic alarmism is justified, because there will be a warming, but not a significant one, a moderate one that we can adjust to it rather easily. Okay. Now, this is what we can get from these models. This is what we can get from these models. Okay, so from this scenario. So if we remain here, I don't think that the alarm is justified. But we would like to do something more than this. We would like to really test whether or not the models are correct because of these results that we have discussed before. So there are evidences from alternative temperature reconstructions that the models might be wrong. So all models might be wrong. If this temperature, satellite temperature, are right, all models are wrong. So there should be something some big problem here, some physical problem that is not solved yet. And therefore, we need to test whether these models are really correct. So let's go back and let us introduce this new topic. And what is here? So what is here? So we would like to understand the origin of the global warming theory, the thesis that the humans are causing an anomalous warming. Now, it is important to notice that before 2000, Earth scientists usually believed that during the last centuries, humans might have contributed no more than 50% of the global warming. And then we had natural variability. However, in 2000, the IPCC published this record. This record is known as the hockey stick by Michael Mann. And this record were claiming that the temperature of the Earth had remained nearly constant for about 1,000 years. And then since 1900, the temperature started to rise very, very fast. So this graph was interpreted by the IPCC as a empirical demonstration that the warming that we observed during the 19th centuries was anomalous. And the only thing that had a similar shape were the CO2 emissions, the anthropogenic emissions, and therefore the IPCC interpreted this graph as demonstrating in some empirical way that humans were actually causing climate change, and in a very alarming way. The problem, however, is that as the IPCC advocated this graph in 2001 and then in 2007, but then in 2013, the IPCC did not use anymore this graph, because in the meantime, this graph was demonstrated to be erroneous by several people. In 2013, the IPCC published this graph, and where it shows several alternative reconstruction of the climate of the past, created by several groups. And now these graphs show a climate change very different from the hockey stick. So now it appears a significant change, natural change of climate system. So we can see a significant warm period during the medieval time. Then we can see a relatively cold period known as the Little Ice Age, and then a new warm period during the last century. And this graph is very different. So, for example, if we compare these two graphs, here the difference between this temperature and this temperature, so during the medieval period and the Little Ice Age here, is about 0.2 Celsius. So here we have 0.2 Celsius, so we have 0.2 Celsius about of difference. But here, if we see the difference here, the temperature between, let us say, from this point here to this point here, it is obvious that the difference is much, much bigger. Is much, much bigger. So we have 0.8 Celsius of difference between the medieval warm period and the Little Ice Age. So it's 4 times more than what is shown here. And why it is important? So this is one of the records. So this is one of the records that are shown here. Okay, this is one of these records. It's this record here, actually. It's this record here. So this record shows very clearly a cycle, a millennial cycle. So we have a Roman warm period. Then we have a Dark Age cold period. And we know this from the fact that during this period, some people from North Europe invaded the Roman Empire. Okay, so probably because the winters were too cold. And then we had again a warm period, medieval warm period, followed by a new ice age, a Little Ice Age, so a cold period. So the temperature fell down very, very fast. And then since about 1700, about 1700, the temperature started to rise again. So the warming actually started in 1700, did not start in 1900, started in 1700. So, and this warming does not appear too much different from this warming, or and it is symmetric to this cooling. Okay, so these new graphs suggest a significant contribution of natural factors influencing climate change, which this reconstruction were denied, because this reconstruction were telling us that natural variability practically did not produce any warming, almost any warming. So this reconstruction is compatible with the climate models. The climate models we have seen before, the climate models were predicting that natural variability did not produce too much climate change, so it's very modest. So this record is perfectly compatible with the predictions of the models, but this data show a different story, prove a different story. So it proves that there is a natural variability that is very significant, and that the models are not able to produce. Now, regarding the medieval warm period, we have a lot of evidences. So, for example, we know that the Vikings went to Greenland during this period, and they actually had villages in these regions. They had villages in these regions in Greenland. They were grew barely in south of Greenland. This is a constructions, a Viking constructions. So what we see from this photograph is that in this area, in this region, there are no trees. There is no trees at all during this in this place, but it is very likely that at the time these villages were surrounded by some kind of little forest or a little bit of wood, because they needed some wood for living. Okay, so they had ships, for example. These ships required wood for be fixed and so on. So it is not credible that Vikings created the villages where they could not get some wood. So today, very likely these regions are colder than at the time of the Vikings. So, for example, in this point of Greenland, there is this valley. This is the only part of Greenland where there are some trees today, and very likely, all these regions where the Vikings were living at the time had to look like this region. So they needed to have some forest. They need to have some tree around, because they needed the wood for surviving. We have other evidences of medieval warm period. So, for example, this is the temperature of the Alps. This is a reconstruction of the temperature of the Alps. So we have here the temperature is more or less today. And then we had this little less ice age, and then we have the medieval warm period where the temperature probably was a little bit higher than today. Then we had this cool period, and then again we had this warm period. This warm period here occurred around 300 years before Christ, and this is when animals crossed the Alps, and with elephants and a big army, and it crossed the Alps where today there is a glacier, so it is not possible to cross the Alps. And then we had other cold period, other warm period, cold period, warm period. and so on. So then until we arrive here, so this is the optimum of the Holocene, is the optimum of the Holocene, where very likely the temperature was significantly higher than today, and the glaciers were much smaller than today. So this is the time of the Tyrolean iceman that was found in the Alps. This body is a mummified body. This is a mummified body, which means that at the time there was no ice around, because a body, so this is not a frozen body, it's a mummified body. So to have a mummified body, you need to have a dry weather, a dry weather. So this means that when this man died, this place did not have any glaciers. Then the glaciers came later, and so and then when now the glaciers disappeared, the body was found under the glaciers, essentially. So we have other evidences of warm period in the Alps. So practically we are able, so a lot of wood has been found in places where today there are no trees, because it was warmer. Because it was warmer during this period, okay? It was warmer and the trees were growing at higher altitudes. So you can find the wood in places where today it is too cold for the trees to grow. This the scientist Christian Schluchter is one of the most important experts of the climate of the Alps, and he believes that during the Roman period, the pass of Susten in Switzerland, the pass of Susten, which is this one, had to look like this picture. So today this pass looks like this. You don't see any trees around, but in this place you can actually find trees, rest of trees. So so it believes that during the Roman times this place had to look like this, with trees, with little forests and so on. So little ice on the mountain. Instead, today the glaciers goes down and so on. So you have this kind of situation. Now, but how do the models are able to reproduce this data? The models are not actually able to reproduce this data. So, for example, the models here produce this red line. This red line is one of my reproduction of climate change during the Middle Age. And so what we have here is a warming period. And then we have the models are here. The models are here. So the models actually were not able to reproduce the warming during the medieval period. So we have that the models more or less appear to agree during the last 100 years, but they fail completely during the medieval period. So they don't get the warming. This is important because this means that the models do not have the mechanism necessary for reproducing this warm period of the past. And actually the models are not able to reproduce any of these warm periods that we have seen here. So there is they do not reproduce this warm period. They do not reproduce this warm period in these places. And therefore, this was one of my study here, but this is not just what I found, because here in this picture we can see This is a picture, figure 3.2 of the IPCC AR6. So at page 432. So here the IPCC show their picture where they compare the models. They compare the models against the data that they use, the new data they use. So the data are this gray area. The models, the latest models are this one, the CMIP6 models. These are in red. And what we see in this picture is that the models are here. The models are here. The models produce this warming here. So the models are in this range. The models occupy this range during the medieval period, okay? They occupy this range here. The model occupy this range here, while the data are the black one, the gray one. So it is evidently warm. So the data show a significant warm relative to the prediction of the models. So again, if we look at the IPCC picture, we have a clear impression that these models are not able to reproduce the medieval warm period. So these models are missing some very important mechanism capable to reproduce a warm period in the past, so they don't have the right physical mechanism. And this implies that we cannot trust what is happening during the last 100 years because the models may be producing a warming, but for the wrong reason. So we have seen here that this warm period are more or less regular. So we have today, we have 1,000 years ago, 2,000 years ago, 3,000 years ago, 4,000 years ago, 5,000 years ago, 6,000 years ago. So we see that every about 1,000 years, we have a new warm period. So it is regular. So we could actually predict, and actually it was predicted in the past, that this period should have been warm. And so it is a regular pattern, it's more or less a regular pattern. So it is very likely that this warm that we have seen in the last centuries is part of this oscillation, of this 1,000-year oscillation that we have seen here very clearly in this record. So, but the models are not able to get this oscillation. The models produce this warming, and then produce something that more or less is constant like this. So they don't get this warm period of the past, which implies that the models are missing some very important ingredient of climate change. And this picture produced by the IPCC clearly, in my opinion, demonstrates that these models are not correct. Now, what is causing this oscillation? What is causing this oscillation that we have seen here? So the models do not have something. Now, the only forcing that is able to that presents a 1,000-year oscillation is actually solar activity reconstructions. So these are some alternative solar activity reconstruction. This is the temperature reconstruction of England. So the black lines are the central England temperature. The red area here is a proxy model, of the temperature of England. So what we see here is that we have this medieval warm period, this little ice age, and then the current warm period. And the only thing that more or less looks like the 1,000-year oscillation of the temperature is solar activity. Therefore, it is evident to me that models are not modeling well the solar impact on climate change, which is evidently very important. And this is clearly seen, for example, in this picture. So here we have a reconstruction of a more recent reconstruction of the total solar irradiance. So we have the sun has been high during the last century, then has been relatively low during this period, and then we have high solar activity during this other period, low solar activity during this other period, high solar activity during this other period. And this is a reconstruction of the climate change. So we have the modern warm period, the Little Ice Age, the medieval warm period, this ice age, Little Ice Age during the dark periods, and then we have the medieval warm period, which is here. So here is again a reconstruction of the summer European temperature, published in 2016. So we have here the temperature in 2000, which are here. And then we have this Little Ice Age here, this medieval warm period during this period, then this period of relatively cold, this warm, this cold, and then this warm Roman period, with temperature that were actually higher than the temperature in 2000. Okay, so we have this peak here that is clearly warmer than this peak here. So we had this very warm period. So again, we find this nice 1,000-year oscillation, which here is also clearly evident. And only the solar activity, solar records match this pattern, this 1,000-year pattern. So actually, we can see this oscillation in many records. This is a reconstruction of the Greenland, temperature in Greenland, 2004. So you see these periods of warming period that occur more or less every 1,000 years. So you can see this oscillation. And then here you have the optimum of the Holocene, that is this warm period that we had about 8,000 years ago. So we have many periods, very warm period. And we had many papers that show a very good correlation between climate change and solar activity. So here we have, in blue, we have a reconstruction of solar activity produced by C14. And then we have a black line is one climatic record. Here we have another paper and here again we have a reconstruction of solar activity that is blue, and a record based on oxygen 18, and we again see a good correlation between the two records. So this kind of papers suggest that climate change has been mostly regulated by solar activity. And this has been always so. Therefore, the claim that solar activity actually has a very little impact on climate change is not credible. Then we will discuss a little bit more. This is another record. Again, we have C14 here. Then here we have oxygen 18. So we have a solar record, climate record, and you see here a very good correlation. So if we analyze these two records, what we get is that climate records and solar records show the same cycles. So we can see cycles around 46 years, cycles around 60 years, cycles around 90 years, cycles around 200 years, 206 years, and then we see the 1,000-year cycle that we have discussed before. And then there are other cycles. But what are these cycles? What are these cycles? Now, here I don't have time to discuss in details this issue, but actually these cycles, these 45, 60, 90, 206, 1000 and so on, are all astronomical cycles. So these red dots that are here, these red dots that I put here, are actually the main resonances of the solar systems. So the solar system is actually oscillating, and it's producing several cycles because for a very simple reason, because the planets are moving around the sun, so they produce a lot of gravitational oscillations. So these are the gravitational resonances of the solar systems, which, according to my interpretation, so for example in this paper, these oscillations are regulating both solar activity and the climate on the Earth. And we see that these gravitational resonances are clustered in exactly where we found the typical oscillations that characterize both solar activity records and climate change record. The longest cycles of this group is this one. This is a cycle of 2,318 years. This is known as the Bray-Alps cycle. Practically, we have in blue, we have in black. In the black is the record of C14. So it's a solar record, C14. In blue, we have the resonance, the gravitational resonance, which produces this 2,318 year cycle, so which reproduces the Alstat cycle observed both in solar and in climate records. So we have that these records show us that there is this strong connection between solar activity change and climate records. So we need to understand how the sun influence the climate system. Okay, so we cannot ignore this coupling, this effect. Now, there is some problem here. So I would like to discuss this issue, how the sun acts on the climate system. So we have that the models adopted by the IPCC believe that the role of the sun is marginal. So it's very, very small. It's a very, very small role. However, we have many empirical evidences. So we have empirical studies that suggest that the role of the sun is dominant. So we have a problem here, okay? Because the models tell us that the sun does not matter, while many empirical evidences suggest that the sun is important. So how do we solve this apparent contradiction so between these two results? There are two possible solutions. So the models may be using erroneous solar forcing, or the sun may be acting on the climate through mechanisms that are not related to radiation. So mechanisms that are related to the magnetic activity of the sun. So, for example, the magnetic activity is known to modulate cosmic ray fluxes acting on that fall on the Earth. Okay, so perhaps the sun is acting on the climate not only because its luminosity changes in time, but also because its strong magnetic activity can generate some kind of corpuscular forcing, so cosmic ray, solar wind interplanetary dust fluxes and so on, that can eventually influence the Earth system. And the models do not have any of this, do not have any of this mechanism. Okay, the models assume only solar irradiance. Now let us understand a little bit better this issue, because the IPCC in general, the climate models claim that the sun is not capable to interpret the observed climate change. The traditional argument that is presented here is the following one, that is given by this picture, that is a picture produced by the IPCC. So practically, we have the effect of a different kind of forcing on the troposphere, in the troposphere and the stratosphere of the Earth. So this is the whole vertical profile. Now, when the models are forced only with solar irradiance, an increase of solar irradiance is claimed to produce a warming both at the stratosphere that in the troposphere. Okay, so there is a warming here, this yellow color, which means a warming, the warming should be in both the stratosphere and in the troposphere. This because if the solar radiance increases, also the ultraviolet light increases, and because the ultraviolet light is absorbed in the stratosphere, in the stratosphere, then an increase of solar radiance should induce also an increase of the temperature of the stratosphere. However, if only greenhouse gases are adopted, the greenhouse gases predict a cooling of the stratosphere, of the top of the stratosphere should be cooling. So we have this color here. Okay, so the top of the stratosphere should be cooling instead of warming. So we have a big difference between a solar effect and a greenhouse gas effect. Here the stratosphere warms, here the stratosphere cools. And what is actually observed is that the stratosphere has been cooling a little bit, And therefore, those who believes in this interpretation claims that the sun could not have induced the warming of the troposphere, because the troposphere is cooling as the greenhouse effect would predict. Okay. However, this interpretation excludes the sun as a possible main driver of the warming of the troposphere. Because if the sun was a main driver of the warming of the troposphere, also the stratosphere had to warm, but we don't see that. Okay, we see a slight cooling of the stratosphere. Now, this argument that appears strong indeed is not solid, because in this modeling, this climate modeling, here the sun is supposed to act on the climate system only as irradiance, only as total solar irradiance. So like UV is irradiance, okay? But what we are observing, what many people observe, is that the sun may be acting through other mechanisms, not through irradiance, but through mechanisms associated with the magnetic activity. And these mechanisms are not included in this simulation. So this argument does not hold. It's not correct. In fact, let us see how cosmic ray may be acting on the climate system. the cosmic rays, the cosmic rays are coming from outside the solar system. They're coming from the deep space because they are produced by stars that explode, okay? So they were supernova stars. Then cosmic rays are made by particles that are charged particles, okay? So are ions. And these ions can be deviated by the magnetic activity of the sun. So when the magnetic activity of the sun is very, very strong, then the cosmic rays are deflected, so they don't reach the Earth. When the solar activity is weak, so magnetic activity is weak, the cosmic rays are able to enter inside the atmosphere in greater quantities. Now, when the cosmic rays enter in the troposphere, they break the particles, the molecules of the atmosphere, and they ionize the atmosphere. And the claim is that this ionized troposphere is able to produce more clouds. Therefore, when the sun is strong, cosmic rays are low, we have a less cloud, and therefore we have global warming. When the solar activity is low, we have more cosmic ray. More cosmic ray means more cloud, and therefore we have a cooling of the surface. And we have many evidences that a mechanism like this may be working because, for example, we have this Ford-Bush, the response of the cloud system to the Ford-Bush decrease. The Ford-Bush decrease occurs when there are big explosions in the sun, so there are big magnetic storms in the sun. When this happens, cosmic ray decreases very, very rapidly. Cosmic ray decreases so when there are big events, so we have solar wind is very, very strong. So solar wind deflects a cosmic ray. And therefore we have this decrease of cosmic ray. And after that, also the clouds decreases. Okay, so this is the red line are the decrease of cosmic ray, and after a few days we observe a decrease in cloud cover, Okay, therefore it seems that the effect is real, and so we can see also here. So cosmic ray decrease very rapidly due to this Ford-Bush effect, and then after a few days the cloud cover decreases as well. So the sun may be acting indirectly on the cloud system through corpuscular forcing, by modulating some kind of corpuscular forcing. Now this effect will happen in the troposphere. Here this is an effect that happens here. Is in the troposphere. So the stratosphere is not involved because here we don't have clouds, and therefore this simulation would be wrong. So the sun also would warm the troposphere, but not the stratosphere because of this other mechanism, So this issue. So this is maybe this different forcing, Now, when we talk about solar activity, okay, so the sun may be acting on the climate in different ways. However, we still need to know what happened to the sun in the past. And unfortunately, we do not know what is truly happening in the sun. So what we have in this picture, for example, is a record, are several records of total solar irradiance, So we have these records. There are few records. Some records show a very little variability, solar variability. Other records show a very big solar variability. Also here we can see there is a huge differences between the science groups, teams that study how the sun have changed in the past. So there is no agreement at all among the solar scientists. Also during the last 40 years, there are problems with the actual observations, solar radiance observation, total solar radiance observation. So we have the ACRIM group, which have predicted a warming and then a slight cooling. And then we have the PMOD group that predicts this continuous cooling, a slight cooling of solar activity. So it is clear that if the ACRIM group is right, the sun has increased from 1980 to 2000 and then decreased later. If this group is right, the sun has decreased. So this has implications also for climate change attributions, because we have seen during this period, we have seen a warming. So therefore, ACRIM will actually correlate with the warming, but the PMOD reconstruction did not correlate with the warming. Now, I don't have time to explain the difference between these two groups, but essentially, the ACRIM group uses the data as they are published. The PMOD group alters some data. So, for example, it is clear here, these are the data. These data are going up during this period. This is known as the ACRIM gap. The ACRIM data are the blue one. So this is the ACRIM gap. So this record is going up. Here, this same record is going down. The reason is that PMOD alters this satellite data for some reason. Okay, but these are the data actually published in the literature. These are data who were not published by the experimental teams. These are modified data by the PMOD, who claims that this data should be modified, but it is not possible to validate this modification. So in any case, we have a lot of problems regarding what happened to the sun. So, for example, here I am comparing different reconstruction of solar activity. So we have this record here. These records here show a very low variability, secular variability. It's very, very small, the variability. So you see this number here, very, very small. This record show a bigger variability. This record is another group that show a bigger variability of solar activity. So here we have different bats. So here we have just from here to here, we have just one bat. Here we have from here to here, we have 1, 2, 3, 4, 5 watts. So we have 5 times bigger variability, secular variability than between the record and these records. Now, so what I did, this is one of my latest paper, was to combine this reconstruction together. And if we combine this reconstruction together, we get different possibilities, okay? So we get this different possibility. So we have this green curve. This green curve is obtained from these records here. This green, and then these other curves are obtained from combining these other records with higher variability. Now, what is the difference? So we see here that the green curve is actually what is used in the climate models. What is usually used in the climate model? So you see this solar forcing. This is solar forcing, and instead these other curves is what one gets from the other solar reconstruction available in the literature. So we have this big variation. Okay, so if you use the green curve, the climate models claim that the sun did not cause too much warming. In fact, the green curve more or less is almost constant for 100 years. So there is no big difference. So practically this level here is more or less equal to this level here in 1900. So here we have the latest data. So it is clear that if you use the green curve, the sun should not have induced any real warming because more or less remain constant. Instead, if you use this other forcing, what you see here is that solar activity has increased during this last 150 years. Okay, so and it has also a nice modulation. So because here the solar activity goes down, then it goes up, then it goes down again, and then it goes up, and then it goes a little bit down, and so we have a secular increase, and we have a multi-decadal oscillation. We have a multi-decadal oscillation. Here, instead, we have the volcanic forcing and the anthropogenic forcing used by the models. Therefore, we need to interpret the climate change using this data by considering that there is a huge uncertainty regarding the solar records. It is obvious that if we use only this record, the green record, solar activity did very little. And this is what the IPCC claims. The solar activity does not matter. Now, the models are actually run in two different ways. So in my paper, I use these records in different ways. Let us, in the first case, we suppose that we have this anthropogenic forcing, this volcanic forcing, and then we use the green solar record. And we get this kind of simulation. And therefore we have that this is the signature of the volcanic signature. This is the signature of the anthropogenic component, and this is the signature of the sun. So it is evident from this modeling. So this is what usually the models are able to do. Okay, the models use the IPCC claims essentially that the warming is entirely produced by the anthropogenic activity. The solar activity can be neglected because it did not do much, so practically it's constant, so it's very, very little change. Then there is some volcanic activity that is more or less important, that has caused the cooling. So in general, natural variability, so sun and volcanic activity in general could not produce any real warming. Okay, so at the most some little cooling. So 100% of the warming is produced by the anthropogenic activity. But this is what happens. If I use this two forcing and this green forcing, and I am supposing that solar activity acts only as irradiance, only as total solar irradiance forcing. So I am excluding the possibility that solar activity could be acting on the climate using some other kind of forcing, like the one associated with the magnetic activity of the sun. Okay, so what happens if I use this other forcing? If I use this red forcing and I assume that the sun might be acting on the climate by means of alternative mechanism. So, for example, magnetic for related forcing. So, what happens if I do that? I do this. So, the model is able to do something like that. I get this other simulation. So we get volcanic activity, we get solar activity, we get anthropogenic activity. So what we see here is that the solar activity, the solar effect is much, much bigger than this one, okay? Then this one is much, much bigger. The anthropogenic activity is much, much smaller. So here we have 0.5. Here we have 1.3, okay? So we are here, practically we are here. So it went down from here to here. It went down here. It went down here. And solar activity has increased a lot. Solar activity has increased to about 0.4. So solar activity has increased from here to here. Solar activity has increased from here to here. So we have, and this has went down, and this went down from here to here. So with this alternative modeling, therefore, what do we have here? We have that if we allow the sun, so if we use the solar forcing adopted by the climate models, and we make the hypothesis that the sun acts on the climate system only as radiative forcing, which is what the climate model do, no? So the climate model make this assumption. Now we found that sun does not matter much, and we actually found that the equilibrium climate sensitivity of the Earth, of the climate system, could be in this range 1.4 to 2.8 Celsius with a mean of 2.1. So we again find the low equilibrium climate sensitivity range that we have discussed before. So we have found before that by using the models belonging to the low equilibrium climate sensitivity range could be the correct one. Okay, so this analysis confirmed that results. So if we use the forcing adopted by the IPCC models, and we do the same physical assumption that the sun influences the climate system only as radiative forcing, then only the models with a low climate sensitivity model could be correct. So we confirm what we have found before. However, if we do the second hypothesis, so we adopt this other kind of solar forcing, which is deduced from these two forcing, from these two records, with these two records combined. So we get this red one, and we do the hypothesis that the sun may be affecting the climate system not only by means of radiative forcing, but also through other forcing, so related to the magnetic activity of the sun, cosmic rays, so on. Then we find a much stronger solar effect, much smaller anthropogenic effect. And the equilibrium climate sensitivity decreases to this range that is very close to 1 Celsius. To 1 Celsius, at least in this record. In this record, where here, these blue records here actually is a sea surface temperature record. Now I will explain why I am using the sea surface temperature. So if we use these records, the climate sensitivity would be very, very close to 1 Celsius, So while the models, the climate models tell us the climate sensitivity goes between 1.8 and 5.6, this analysis, if we do this other hypothesis, then the climate sensitivity might be much smaller than that. This means that CO2 has a very modest effect on the climate, very, very modest, much lower than what even the low equilibrium climate sensitivity models predict, even those. So this is a comparison between the simulations. So the blue line is the data, this data, global surface temperature data. The red line is the model mean. The model mean. So we see that the model mean produces a continuous warming. And so this green line represents more or less is a sketch of this continuous warming produced by the models. While here is what my model produces. My model produces this kind of pattern. Now it is easy to see that in this second case, what we see is a increasing temperature, but we also see very clearly a modulation that we see here very clearly. So the temperature goes up, then it goes down, then it goes up again, goes down again, and then it goes up. Okay, so we see this warming, which is modulated by an oscillation, which is produced essentially by this oscillation that we see here. Is by this solar oscillation is producing this oscillation. The models instead are not able to produce this oscillation. You see here, because the models here produce a continuous warming. No, the models produce something that is continuously warming, but the temperature clearly goes down. The temperature goes down, and then here goes up, and then it goes down again. So practically, this model, by modeling climate change in this way, which is similar to this way, by modeling climate change this way, we get a much better match between the data and the models. Okay? But to do this, we need to do two things. We need to use a solar record that show a large secular variability, which are excluded by the IPCC, and then we need that the sun is influencing climate system also through a mechanism related to its magnetic activity, which the climate model do not assume, so do not have any mechanism associated to those mechanisms. So we need to have this situation. But so we are able to really get a correct attribution of climate change, which means that the climate system is actually much more sensitive to solar activity changes, and is much less sensitive to anthropogenic forcing, which means that also for the future, climate change will be moderate. For example, this is another my study. Here we do several things. We are studying the natural oscillations of the climate system, and what I discovered is that actually the global surface temperature is characterized by several cycles, which are these lines here. So these cycles are at about 60 years, at about 20 years, at about 14 years. Then we have this signature here, this yellow signature here. This is a solar cycle between 10 and 20. Then we have a 9-year cycle. Then we have a 7.4-year cycle. Then we have these two cycles here at 6.6 and 5.93. Then we have this other cycle 5.2 years. And the interesting thing is that all these oscillations all these oscillations that are here were found also in the natural oscillations of the solar system. So in the solar system, we found the gravitational oscillations associated to 60-year cycle that correspond to this cycle in the climate system. We found oscillations around the 20-year cycle, and we found this here. We found an oscillation around the 14-year cycle, which is this one in the climate system. Then we found these two oscillations that are between about 10 and 20 years, which are probably, according to other models, are related to this oscillation here. This is sunspot, the 11-year sunspot cycle, which are generated by these two oscillations. Then we have here, we have a 9-year cycle in the temperature that we don't find here because this is a lunar cycle. This is a tidal cycle. Then we have the 7.4-year cycle, which we found here. We found here. Then we have these two cycles here. And we found these two cycles here very clearly, and so on. So practically we have that all oscillations observed in the climate system are found also in the gravitational oscillation of the solar system. And very likely this means that the climate system is regulated by astronomical forcings. And therefore it is possible to use these oscillations for constructing a harmonic model of the climate system. And this is what we produced. I produced with this harmonic model using many of these oscillations. And I compare these predictions with the predictions of the climate models used by the IPCC. So you see here that these models are of course, showing too much warming, and then they explode in the future. So they predict this huge warming in the future. While if we consider natural oscillations associated to astronomical forcing, the anthropogenic contribution will be more moderate, and the temperature will rise much less. We reach much less compared to this prediction. So in the future, the climate will be warming, will likely be warming during the 21st century, but in a moderate way, that should not be particularly alarming. Should not be particularly alarming because for 2050, for 2050 here, the temperature will be well below. The temperature will be well below the 2 Celsius degree. 2 Celsius degree. Therefore, there should be no big problem. There should be no big problem. So we can adapt to climate change if the temperature grow slowly. So we can adapt to climate change. So there is no alarm. Instead, here the alarm exists. Here the alarm exists because you see here that 2 Celsius degree are crossed in 2040. Okay, 2 Celsius degree are here. So these models predict that the 2 Celsius warming will be crossed by 2040. So we have in 20 years we will rise, but here no. Here we need to wait 2070, 2080. So it's very. We have much more time to adapt because the temperature will not rise so fast. So there is no alarm. And now there is another topic here, because I told you before that there is a problem with the global temperature record, because the satellite records show a much less warming than the global surface record. So if this is true, then the models should be all dismissed, because we need new models. Completely new models for interpreting climate change. Now, is it possible that the global surface temperature, so this warming here, is biased? is biased? The answer is yes. It is possible that it's biased, and because the surface records might be influenced by urban heat islands, by the warming induced by the cities, for example. No, so during the last 100 years, the cities has grown. And therefore, the warming produced by the city has grown as well. And this, and because the meteorological stations often are close to urban area, practically almost all meteorological stations have registered a warming which is related to the urban heat, instead of being related to the global warming, real global warming. And therefore, it is possible that the global surface temperature, like this one, which are produced by using the record measured in the weather stations, maybe keeping some warming from the cities, which they are not able to clean up. And we can see that this is the case, for example, by comparing the urban and rural stations. So if we produce the record of the land record by using both urban and rural station, we get this red record. But if we use only the records from the rural area, we get these blue records. And what we see is that there is a clear, the warming is much less. The warming is much less, which is more or less comparable with the difference in warming observed between the surface temperature record, which are red, and the satellite, low troposphere satellite record of this group. So there appears to be some contamination from the cities in this strong warming. This can be also observed in this picture. Here I am comparing the land records. The land records, these are the global land records. These are the satellite records above the land. And you see this big difference between the two records. So, but if we go over the ocean, the two records more or less agree. The two records more or less agree. Therefore, it is possible that this disagreement that we see here is due to urban heat and not to global warming, real global warming. Okay, this means that this warming here may be exaggerated. This might be the right warming, and this means that practically all climate models are wrong, and therefore they cannot be used to do prediction for the future. We need new models. And today we have a very strong evidence that the low troposphere warming is rather low, because we have two records, two low troposphere records that agree with each other. We have the UAH MSU records. This is the Roy Spencer and Christie records. Instead, this is the NOAA record, the STAR version 5 record produced by NOAA. So these are produced from the satellite records, and these two records agree. So the warming here of this record is 0.41 Celsius. The warming here is 0.38 Celsius. So this actually is a little bit colder than this. So these numbers are rather lower than what the surface temperature record show. The surface temperature record show something close to 0.506 Celsius, while the satellite records start here are much lower. So that means that this, and we have two records. And then we have seen before that according to the models, the temperature in the troposphere should be warmer than the surface. So this means that this might actually be the real temperature of the surface. So something around 0.4, which means that the climate sensitivity should be reduced by 1/3, and therefore again we find something compatible with what we have found using the high variability solar records and the hypothesis that the sun could be influencing climate change. So these records would be compatible, very well compatible with this modeling here, that is here. Therefore, we have this interpretation of climate change. The sun is very likely strongly underestimated. The climate models are surely they contradict each other, and very likely they are predicting too much warming, which means that they cannot be used for doing projection for the future, and therefore the climatic alarmism is not justified by these results. And so what can we do here? From economical point of view, now I would like to do just a few minutes for introducing the economical issue, because from a scientific point of view, I don't think that the anthropogenic global warming theory is correct, because it's not able to, these models are not able to correctly interpret what the sun is doing on the climate. But from economical point of view, people are making policies based on these climate models that we have seen that they are not credible. This policy suggests that we need to reduce the emissions by 2030 by a large percentage, and then we need to reach the zero emission by 2050 to save the planets. We need to save the planets because according to these models, this is what is happening, okay? According to these models, is this what is happening? So we will cross the 2 Celsius degree in few years if we do not mitigate significantly climate change. So these points are derived from this simulation, from this prediction. The problem, however, is that even if that interpretation of climate change is correct, it is not likely that humans will be able to reduce the emissions. This is because while, for example, Europe is reducing the emissions, and the same thing also is doing, United States are doing the same thing, is they are reducing a little bit the emissions. The rest of the world is increasing the emissions. So practically Western countries are reducing the emissions, but everybody else is not doing that. And the Western countries are only a small percentage of the so the emissions from the Western countries is a small percentage of 20%, about 20% of the total emissions of the world. So if the rest of the world is increasing the emissions, there is no way to reduce the emissions, even if we decreases them. And this picture suggests what is happening right now. These are actually power plant fired by coal. Okay, these are the power plant, electric power plant that are actually that are being built right now. We see that in the Western country, there are no power plant with coal, but in the Asian country, for example, in the Asian countries, there are hundreds of coal-fired power plants under construction or are planned. There are hundreds. So practically in these regions, every 3-4 days, there is a new power plant that is built. And therefore, this picture shows us that Asian countries, in particular Asian countries, are not reducing their emissions, but they are increasing them greatly. And so Asia, India, but also Japan, Korea, no? They are all countries in Indonesia. So practically everybody here is increasing coal-fired power plants, which means that there is no way that we can reduce the emissions. So these things here is not credible. So this is completely absurd. But we are doing that in Europe, in America. We are doing that. So in the United States, we are doing that. So the effect would be only to move the production from Western countries to China or India. Okay, the production will move from Western country to India or China. So we will get poorer, and the Asian countries will get richer because they will have the total production. So they will produce everything. So we will buy things from China and India, essentially, and get poorer and poorer. Another thing that I would like to address is this topic, a very hot topic now. We have this electric car. We have the electric cars that people are sponsoring to save the planet, decide to save the planet. But many people do not know that the electric cars were actually the first car that were invented. So in the 19th century, they were invented the electric cars. These are pictures of these electric cars. And these are Ford Motor, for example, in the United States, we had this Ford Motor company, that were building these electric cars. And they practically had, more or less, they had the same thing that today they have, no? So cars that had a big problem, because the problem was the battery. The problem with the battery is that has not been solved yet. So these cars could not compete with the gasoline car because the batteries required to be charged, and so with all problems that we had. So, and therefore this technology is a technology that was already invented more than 100 years ago, and it failed because all these companies, all these things, then bankrupted because they could not compete with the gasoline cars. Okay, so this is already old technology. It's not the future, but actually it was the past. If we do not solve the problem of the electric batteries, and we do not solve the problem of how to produce the energy, that essentially we need a nuclear plant to produce all the required energy. So it is clear that this technology will not save the planet, also because it requires a huge amount of minerals and so on. So it's very polluting technology. It's not so clean as people think. So it's very polluting technology for many, many things, and it has a lot of problems associated with the batteries. So the electric motors works very well, but only if you have trains or trams, so all things that are connected with lines. Now they get the electricity from the lines. So in that case, they work, but if you need batteries, these things have never really worked well, and so it's all technology. Then they have other things with this renewable energy, solar panel, wind turbine, and so on. So all this technology does not work well. And not only does not work well, but it is very polluting too. So we have so because they last 20 years, 25 years, then they break down, or for several reasons. Here there was a tornado that destroyed a solar plant in this way. So these are very, very, they don't work well. So this cannot be the future, So we are spending a lot of money by hoping to save the planets, while West Asian countries are doing the exact opposite, and so it's not very wise. And we are doing all these sacrifice because we believe in climate models. We believe in these climate models here, simply because we believe this climate, but this will not be real. This is not real. This will not be real because the climate seems to be characterized by oscillations, by solar forcings that are not considered today. So the warming will be much more moderate. So all this sacrifice will not be justified. And so it is used. In conclusion, the models on which the anthropic theory of global warming observed from 1850s based are not scientifically validated. So this is what they are not scientific. They contradict each other and therefore cannot be considered reliable for future climate forecast, according to various initial scenarios proposed by the IPCC. So what we have from historical paleoclimatic evidences is that the natural climate variability induced by the sun and other astronomical factors is much more important than what the IPCC model are able to predict. So this means the models are wrong, okay? And the inclusion of natural climatic cycles and non-climatic forms of warming is UHI, urban heat island, as an effect of reducing anthropogenic component associated with CO2 from 50 to 70%. So in my opinion, the observed warming from the pre-industrial era is 50% due to the sun, is about 50% is due to the sun. 30% is due to anthropogenic emissions, 30% to anthropogenic emissions. And there is another 20% that is spurious because it's due to urbanization, urban heat, which are not climatic warming, something local that occurs so it's spurious, so it's not. So in my opinion, this is how the real warming, so 50% sun, 30% anthropogenic emission, 20% is not real. It's not real. The IPCC instead believes that 100% is due to humans. And therefore, all alarmism is related to this belief, which, in my opinion, is not justified by the analysis. Okay, so I finished here.
Fantastic.
Okay.
Thank you for all your time. That was really good.
Okay, bye-bye.
All right, talk to you later. Goodbye.
Bye.